Good afternoon, everyone, and good morning, I believe, in UK, Dr. Chakrabarti. We have Dr. Barun Chakrabarti for our non-open webinar today. I would like to give a brief introduction before giving the screen to him. Dr. Barun Chakrabarti received his engineering degree in chemical engineering at Imperial College London and a PhD on regenerative fuel cells at the University of Manchester. After a year of industrial experience in biodiesel development in UK, he became an assistant professor in a technical university in Pakistan and later in University of Malaya in Malaysia, focusing on biodiesel R&D and electrochemical wastewater treatment. In 2012, he returned to Imperial College London as a postdoctoral research fellow, and later moved to Warwick Manufacturing Group at the University of Warwick, where he currently holds a position. His research focus is on hydrogen-based redox flow cells, flow batteries, electrospinning, electrochemical regeneration of lithium-ion battery cathode materials, and electrophoretic deposition of nanomaterials. And today, he's going to talk about the electrophoretic deposition to enhance the electrode performance in hybrid, hydrogen-based flow batteries and supercaps. Dr. Chakrabarti, screen is yours. You can start sharing your screen and start the seminar.
Okay, so thank you very much, Dr. Serap, for the very nice introduction. Good afternoon to everyone. Although it's good morning here, but it's afternoon for the viewers, I guess. So yes. I'll start sharing my screen and without wasting any more time. Right. So the topic of my presentation, I think, has already been well advertised. I've seen this also in the LinkedIn as well as very nicely profiled. So many thanks to Sunum and Sabanji University for advertising this talk very nicely for me. So I'm going to talk about my current research in the last few years, focusing mainly on electrophoretic deposition to modify electrodes for electrochemical energy storage applications, focusing particularly on flow batteries and later on in supercapacitors. Although I've given the title in a different manner here, like actually my talk is going to show first flow batteries and then supercapacitors. So it's the other way around. So without much ado, the summary of how I'm going to layer this talk. Hopefully everyone, before I continue, everyone can see my screen. Is it clear and visible for everyone?
Yes, it's clearly seen.
Okay, that's good. Yeah. Okay. So carrying on. So I don't know how many people would be knowing about electrophoretic deposition. So assuming layman knowledge, I'm going to give a bit of introduction, but not too much, because there may be some people who may get bored by who may be knowing about it. So I'll try to be in between here. So not too much, but sufficient detail so that people understand what it is, and then what a flow battery is, and then why there's a hybrid type of system as well. That also needs to be defined. And then, of course, I've seen that in Sabanji, you're doing research in supercapacitors, so I don't want to go into defining this too much, but still, I will have a brief introduction to this. And then I will go on to my particular studies on how electrophoretic deposition has improved the performances of the hybrid flow batteries in my research, and then how electrophoretic deposition has improved performance of supercapacitors in my research as well, both for coin and pouch cell studies. So carrying on, firstly, the Epd Principles. So this is a diagram from one of my latest papers in RSC Advances. It shows the principle of how when a power supply is used to supply a high voltage in a colloidal suspension of charged particles, it can force a selective migration of these particles onto a particular electrode, which can be known as a working electrode. And you can deposit these particles onto the surface, and you can have different porosities and tortuosities and so on. And you can have a very compact layer of deposit, which can be an electrode material. So although electrophoretic deposition appears simple, it has many different factors. So it's not very easy as it appears. So for instance, temperature can affect the migration of these particles. Stirring of the electrolyte, or maybe how if you keep it still, can affect it as well. The type of counter electrode being used, whether it's if it's corrosive to the particular solvent, it may also affect the process, and there are so many other such factors, and so on. This is the diagram for the electrophoresis that I did for making supercapacitor electrodes, which I will be discussing later on, the results and discussions. The work I did for flow batteries, it's a slightly different modified setup. This is a classical EPD setup where you have a vertical type of reactors, and you have controlled migration going on either this direction or that direction, doesn't matter. But in the case for the flow battery, it's a horizontal setup. It's a different style, and I'll discuss that when in due course when I come to the flow battery descriptions. So as I mentioned before, the EPD process requires colloidal electrolytes, which are electroactive as well, and sometimes additives are also added such as binding agents to ensure that the electroactive species stick onto the surface of the foil, for instance, aluminum foil, and also charging agents to enable easy transport of these particles onto the working electrode. Electric current is usually, it says electric current, but you actually need to have almost zero electric current in this case, and usually high voltage, especially if you're using non-aqueous or organic electrolytes. However, if you use water, you can restrict it to 5 volts or so, and you can have a reasonable deposit of particles onto your foil or surface on which you're going to prepare the electrodes. And after the electrodes are prepared, the drying step is usually quite reasonably fast compared to if you're doing a classical slurry cast method of using NMP to deposit active materials onto an aluminum foil to prepare either lithium-ion batteries or electrodes or supercapacitors. They require quite a long time to dry the NMP, so it's quite an energy-intensive process. Whereas in this case, the solvents for EPD that we use, like alcohol or acetone, for instance, they dry off very fast, so it's less energy-intensive. And also, finally, step 4 is you can either use the electrodes as they are after they're prepared, and they can give reasonable performance, or you can calendar them like hot pressing or cold pressing to ensure better electrical contacts between the electrode surface and the aluminum foil, and you can get usually better performance by calendaring. So all these will be discussed in the supercapacitor part of my talk. So prior to that, moving on, what is a flow battery? I think some people may know, and some people would require some introduction to this, and why I'm using the term hybrid for flow battery. This also I'll come to. So in general, a redox flow battery is if you can think of it's like a hybrid between a battery and a fuel cell. So you can, it's neither a fuel cell nor is it a battery, but yet it's also one of the in between. So the reason it's called battery is because it's an energy storage material. So instead of storing energy in your electrodes, you actually store energy in your electrolytes. This is the major difference. And you store your electrolytes outside of the battery. So when you want to have energy transfer, either charging or discharging, you pump the electrolytes into the power converting module, which is where the electrodes and the membranes are, or the membrane electrode assembly. And you can have charge transport, and you can also have controlled migration of protons or sometimes sodium ions, depending on if you're using a alkaline fuel cell. Then you have to change the migration of the particular species here. It's via the membrane, and via this, because of this unique ability of storing energy in soluble components like all vanadium. For example, you have vanadium 4 and 5 oxidation states on the positive side of the battery, and the vanadium 2 and 3 on the negative side. These are all soluble in sulfuric acid media. So because of this, you can independently size the capacity based on the size of the storage tank to the power output, which is more dependent on the electrodes and the stack and the number of stacks you can have in the cell. So this is an example of a commercially available system. There's quite a lot of work going on in China, for instance, and some in the Middle East, like in Saudi Arabia. There's already 3 gigawatt-hour system being installed, for instance. And because the energy densities of these materials are quite low, they are usually used for large-scale energy storage, or for instance, load leveling for the grid, electrical grid, or for renewable energy storage. Portable applications are much rare because we are still trying to find materials which can have high energy densities, which is still under research. So what is hybrid then? Why are we calling hybrid? So as you remember from the previous slide, I mentioned that the electroactive species are soluble in and usually liquid. So that's why it's called redox flow battery. However, if you have on one half cell, if you can have solid or you can have a gaseous component, then it becomes hybrid. So for example, a common example is a zinc bromine battery. So on the zinc side, you have a zinc deposition onto the electrode surface. So then it's a positive, it's a metal formed, so solid formed. So it's a hybrid in that respect. So a solid liquid system. In this case, what I'm researching on is a gas liquid system. So especially using hydrogen on the negative side of the battery, and on the positive side, I'm using either vanadium or a much cheaper component, manganese. Other systems have also been done, such as hydrogen bromine, which has been researched since the 1960s onwards. But bromine has a lot of toxic properties, and it can also poison the hydrogen side catalyst, the platinum, due to migration via the membrane, which we are not able to yet stop. So more research requires to be done on this. So because of that, bromine usage is kind of limited and it's better to look into other kinds of chemistry, such as vanadium and manganese. But having said that, the hydrogen bromine system is already being commercialized in Holland by a company called Elestor. There's another system, which is the polysulfide air. So all these systems is quite similar to a PEM fuel cell, PEM fuel cell, polymer electrode membrane fuel cells. The only difference is you're replacing for instance, for the hydrogen vanadium, you're replacing the oxygen side reaction with vanadium, or you're replacing the oxygen side reaction with the manganese. So, and you're having the same hydrogen proton reaction as going on in a PEM fuel cell. Or you can also have another system, which is a very low cost and effective system, which is polysulfide air. So you replace the hydrogen side of the PEM fuel cell with the polysulfide reaction. With the oxygen. So you maintain the oxygen side reaction, and you replace with the polysulfide So you have polysulfide and air. So you replace the hydrogen with the polysulfide reaction. So it's the polysulfide chemistry is very complex. So if anyone doing lithium sulfur chemistry will be knowing the issues that you face with this. So even with so this is not a topic that I'll be discussing in this presentation. I'll mainly be focusing on hydrogen manganese and hydrogen vanadium system, and how my electrophoresis has improved the system performance. And basically why we are doing hybrid flow batteries, we're trying to reduce the capital cost for the system. We're also trying to see if we can do system integration with other like combined heat and power and renewable energy storage and so on. And one example of a system integration that we tried to do, and not, I mean, it's a simulated system integration, not practically done yet, is shown in this slide here, whereby it's possible to use wind or solar energy, store the energy when the demand is low in the hybrid hydrogen vanadium flow battery, and supply it when the demand is high and the wind is not available, for instance. Or it's also possible to use energy from desalination plants and also store in the hybrid hydrogen vanadium flow battery. So moving on, this is I think most people will be quite aware of what supercapacitors are, but I'll still have a quick introduction of what they are. There are two types of supercapacitors usually. One involves the ion adsorption on an electrode surface, known as the electrochemical double layer capacitors. And the other one is the pseudo-capacitors, where you have a charge transfer near the surface of the electrodes, which is a typical example shown on the right side here. Usually for supercapacitor testing in industries, activated carbon is the most common material that is used, usually because of its it's quite available, it's inert, and it has very high specific surface area. And usually these electrodes are commonly prepared in the industry via the doctor blade method, by slurry casting, via using NMP as a solvent. And the ratios of the materials are usually this, like carbon black and activated carbon, PVDF, and so on. So what we are trying to do in our research is compare this standard slurry cast method against the electrophoretic method, and seeing if any improvement can be seen, which can be recommended for the industries for supercapacitors. So moving on to my research after, so how did I use electrophoretic deposition to improve hybrid hydrogen flow battery studies? So in this cartoon, I'm showing, like I mentioned in the early part of my talk, that I was using a classical method of EPD, electrophoretic deposition, where you have vertical electrodes. But in this case, for the flow battery experiments, I used a horizontal setup. So the working electrode is kept at the top here, and the counter electrode is at the bottom. And then by applying electrical current, electrical voltage, so trying to minimize the amount of current generated for the EPD, to do a controlled migration of the graphene to the top of the electrode, so that we don't have clustering of the graphene afterwards to form graphite layers. Now, if I had done it the other way around, then by gravity, the graphene would have clustered and formed more graphite, and would have deposited at the bottom, and we wouldn't have had such a reasonable performance, as I will show in the coming slides. So we did both reduce graphene oxide deposition and also nitrogen doped graphene by electrophoresis, and we tested them on the liquid side, or the positive side of the hydrogen vanadium flow battery hybrid system, and also the manganese side. I'm going to skip this polysulfide air side, because it's we couldn't actually do a proper flow battery testing in this, so we're just focusing on these two hydrogen based system. And we compared three systems. So the reason I'm saying as SGL is the manufacturer, a German company, of the carbon paper that we are using, and we have that as a background, and we modified that with reduced graphene oxide and nitrogen doped graphene. So the first results as for the hydrogen vanadium system, usually looking at the current densities, usually a flow battery of a commercial system operates between 80 to 120 milliamp per centimeter squared. So we are trying to see if we can go to higher current densities, and if we can do that, that means we can have lower costs by means of having less like for a stack, less cells in a stack to give similar performance. So we try to go as high current densities as possible to see how the electrodes modified would improve the performance of the hydrogen vanadium system. So usually a vanadium flow battery around 80 to 120 milliamp per centimeter square has a energy density around 25 watt-hour per liter. So with the nitrogen dope system, we are kind of getting slightly higher, and even at higher current densities, the vanadium system goes lower. So maybe around here somewhere, where we are getting higher for the nitrogen dope graphene for the energy densities. And then other figures of merit or key performance indicators for flow batteries is one of them is energy efficiency. So at different current densities, we can again show that energy efficiency is better for the nitrogen doped graphene being sputtered onto the carbon paper by means of electrophoretic deposition. Specific capacity is also better for when we're using nitrogen doped graphene, so we can get much higher capacity. And one of the main reasons for this is because nitrogen doped graphene improves the hydrophilicity, allowing the electrolytes to have better access onto the electrodes and also onto the membranes, and the overpotential is also less. Another key figure of merit or key performance indicator is power densities, which is something taken from classical PEM fuel cell studies. So by doing a standard polarization curve at different current densities against the cell voltage, we are showing that again, using nitrogen doped graphene, we can get a higher peak power density in comparison to standard electrodes, standard carbon paper. Then we did cycling for over 150 cycles and compared two key performance indicators, i.e. the energy efficiencies, how that varied for 3 different electrodes, the standard carbon paper, reduced graphene oxide modified carbon paper, and nitrogen doped graphene carbon paper. And we found that the nitrogen doped graphene paper is performing better in the hydrogen vanadium fuels. Graphene was giving better performance for the hydrogen vanadium system. So we didn't just stop the research there. We just decided to compare with another system, which is the manganese system. And the reason we're using manganese, I'll just quickly elaborate on this, is because manganese is more abundant than vanadium, and then you can reduce the cost of the system significantly by using manganese. But manganese also using manganese on the positive side of the hydrogen vanadium system has its own challenges, because manganese 3 precipitates at a certain potential and then reduces the amount of manganese available for electrochemical reactions. So to circumvent this, to prevent this from happening, we use a soluble titanium salt, which forms a complex with the manganese, and then allows the manganese 3 to stay within solution and be utilized as much as possible for the hydrogen manganese system. So again, first of all, we did the capacity studies for the manganese hydrogen manganese system, and we found that more capacity can be retained when we have a nitrogen doped carbon paper by means of electrophoresis. And then similarly for power density studies, again, just like the vanadium's hydrogen system, we are getting a much higher power density. One thing to note is that standard flow batteries use carbon felts of thick electrodes to have good electrochemical performances. In our case, we're using much thinner carbon papers, which is less porous and so on. But if we modify with the nitrogen doped graphene, we get almost the same power density as with a standard felt used in a manganese flow battery. So we are kind of almost getting similar performance as a standard flow battery for using a carbon felt. Energy efficiency is also better at two different current densities. And this was the first time that nitrogen doped graphene was used in this hydrogen manganese system. So we didn't do more studies at higher current densities as yet, but it is the subject of future work. And also cycling number for 50 cycles. We're also getting pretty good, reasonable maintenance of the energy efficiency for the nitrogen doped graphene, and also the discharge capacity utilization is also quite good. This is at a current density of 50 milliamp per centimeter squared. Charge and discharge. So these are the results, key results that we obtained for the hydrogen, vanadium, and manganese systems. The next thing is just a quick comparison of the costing, a very simplified costing model. So if we have systems like the standard vanadium flow battery, which is the commercialized system, being used for storing electricity for 6 hours, the costing at 3 different current densities shows that the higher the current density is, it kind of goes down, but the costing goes down. However, if we replace one side of the vanadium with hydrogen, at higher current densities, the costing is slightly lower, even though it's not very clear, but still if you project a line from here, you'll see that the cost is lower at higher current densities. And obviously this for the manganese hydrogen vanadium system, hydrogen manganese system, the costing is much lower because the manganese is ubiquitous, it's a much cheaper material than vanadium, more available. So based on this, it's recommended that more studies has done on hydrogen manganese systems, and which is already being done in the UK by a spin-out company of Imperial College called RFC Power. They are trying to make larger stacks of these systems. So hopefully in the future we'll see some prototype reactors being available in the industry for large-scale energy storage. So the next part of my talk is how I modified supercapacitor electrodes with electrophoresis to obtain better performance compared to standard slurry cast NMP electrodes. So the parameters that were used, in this case, we didn't use the horizontal reactor as I did for the flow battery. This is a classical vertical EPD reactor. So the parameters are given here on the left-hand side. The amount of activated carbon and carbon black for improving electrical conductivity. We varied the polymer and charging agents. This ultrasonification was done in order to disperse these activated carbon into the particular solvent, especially because if we leave them lying around for 15 minutes to half an hour, all of them aggregate at the bottom. So it's not possible to then apply electrical charge and make them migrate to the electrode surface. So it's important to use sonication, have them well dispersed in the solution, and then immediately start the process so that we can get as much deposition as possible. These timing and the voltage was selected after meticulous amounts of research to optimize the amount of to get the best deposition of the activated carbon on the aluminum foil. And also we had to keep the bath stirred at this stirring rate and kept at a temperature 40 degrees C. Then of course we did vacuum drying and so on, and in some cases we compared with hot pressing and without hot pressing, and the results will be shown in the coming slides. So some of the key investigations we did was varying the colloidal compositions, the solvents used, whether calendaring impacted the performance or not, and then testing them in coin cells as well as in pouch cells. So the table here summarizes, in comparison to standard slurry cast material electrodes, the various variations that we did in this research for optimizing our EPD performance. And one of them was testing of 3 different solvents. So taking on from the slurry casting procedure of preparing electrodes for supercapacitors, NMP was used, and NMP with its with PVDF and carbon black, and we tried to see how that performance was. So the performance parameters we were testing against was thickness. So within industries, a good thickness should be between 50 to 200 microns. And the other thing is about the adhesion, that does the material stick to the surface. Obviously slurry cast procedure sticks very well, so it's a well proven standard, but EPD doesn't always stick very well onto the surface of the aluminum foil, so we had to test that as well. And the mass loading between 5 to 10 milligram per centimeter square is what's common in the industry, so we try to keep within that range, and also to test the capacitance at 0.1 amps per gram of current density. So we found that from the type of solvents in the first table, we found that the acetone-based solvent using PVDF and iodine as the charging agent was giving the best performance for our research, the highest capacity, as well as the highest mass loading and very good thickness, and also very good adhesion to the surface of the aluminum foil. One thing to note is that these, for example, deposition duration using NMP or with IPA, the isopropyl alcohol, all these electrodes had to be calendared, which is, I didn't mention this here, they had to be calendared, otherwise we couldn't get these kind of performances with them, especially for IPA and NMP. However, for acetone, even without calendaring, we were getting pretty good capacitance and good mass loadings, and they were sticking quite good to the surface of the aluminum foil, the activated carbon, I mean. But if obviously when we did hot pressing, the performance is improved because of better electrical conductivity and connection with the aluminum foil, with the activated carbon and the carbon black. So that's the optimized performance that we got with hot pressed acetone. So here is the other coin cell results. Cyclic voltammetry on the extreme left-hand side, the top side, comparing the different electrolytes for the EPD process against the standard slurry cast method, showing that the acetone solvent with the iodine as the charging agent for the activated carbon particles for control migration, as well as PVDF as the binder, gives the highest capacitance at 20 millivolts per second. And when we did charge and discharge at 0.1 amps per gram, so again, the EPD electrodes using acetone as solvent was giving better performance in comparison to slurry cast standard electrodes. Slurry cast electrodes are performing better than the other solvents, but with the acetone, it was giving much better than the slurry cast. Then we did rate capability studies where we compared EPD from the acetone solvent compared to slurry cast ones, and we found that at all the current densities that we tested, the acetone acetone-based EPD electrodes were giving much better performances, although the performance advantages were decreasing with the higher current densities, but still they were higher than 20% in comparison to the standard slurry cast electrodes. And then we did a Ragone plot as well, where we also showed quite high energy densities and power densities for the EPD electrode from the acetone bath in comparison to the slurry cast standard electrodes. Then from this, we decided to do cycling experiments and compare this cycling experiments at 0.1 amps per gram of standard, the EPD electrode with acetone without calendaring at the bottom and with calendaring at the top. So calendaring was giving us, or the hot pressing was giving us higher capacitances and also better retention of the capacitance over 10,000 cycles. And these are still coin cell testing. So we thought, how would this perform when we scale it up? So to form larger electrodes for pouch cell studies. So the challenges we faced when scaling up were obviously because the reactor for the electrophoresis would have to be bigger. So to maintain the same amount of colloidal suspension as for a smaller bath is more challenging. So we need to have a larger sonication reactor. That sonication time is longer, let's say, for the larger reactor to maintain the same amount of colloidal suspension in the solution for larger electrodes. The temperature and the stirring rate for the electrophoresis and things like that, such factors had to be taken into account to make electrodes for pouch cells. So here are the electrodes that we prepared for pouch cell studies. So it was around 50 centimeters squared, and then when we tested them for standard bending testing, we found that there was no delamination. There wasn't much anything coming off onto the coming off from the electrodes. So it meant that even that when we scaled up the EPD process for producing large scale electrodes, we were not getting any problems for flaking off, and we were also getting quite good performance electrochemically as well, as can be seen here. So when we did about 20,000 cycles at 0.1 amps per gram with the pouch cell, without calendaring the electrodes, without using hot press, we were still getting reasonable capacitance retention. So it shows that this system then that we optimize in our lab can be scaled up and can be recommended to the industry if further studies can be done to show reproducibility. And here we show some cross-sectional SEM images, FIB-SEM image here to show the thickness of the electrode. The reason we are showing this here is because normally, if you look at the literature for electrophoretic deposition for capacitance, supercapacitors of lithium-ion batteries, the electrodes are very thin. They're not as thick, and they give reasonable performance because of the good utilization of the electrolyte within the electrode space at thin layers. But to maintain good performance at thick electrodes is quite a challenge, and this is something that we managed to show in this research. And one of them is probably because acetone is a very good, I mean, it's a volatile solvent. So while it evaporates off, it creates pore spaces within the activated carbon deposits, leading to good electrolyte usage within the capacitance. One thing I forgot to mention is that the electrolytes that we were using was organic, so it's acetonitrile using tetraethyl ammonium tetrafluoroborate salt for all these studies. So that's the reason why if I go back to one of these slides here, you can see that the voltage range is quite high, from 0 to 2.5, and it's not limited by the water windows, water potential window. So with this, I think this is the last slide that I have, and so if there are any questions, you're welcome to ask, and I'll try to answer to the best of my ability. And most of the research has been done in WMG, which is Warwick Manufacturing Group. So you can visit our website and you can have a look at what kind of research we do, and any questions, I'll be happy to answer.
Thank you, Dr. Chakrabarti. And now session is open for questions. You can just speak up or raise hands, or if you like, you can write on the chat box.
You hear me?
Yes, yes, Mayur.
You have electrolytes. Did you use solid electrolytes?
No, I didn't use solid electrolytes. No. All
Okay.
liquid based. Yeah.
Liquids. Okay. How about the hydrogen source? Which kind of source are you using?
At this point, it's still on research stage, so we are using hydrogen from cylinders at the moment. It's laboratory supplied gas cylinders, so it's not yet industrial process as yet. But in future, we would like to do electrochemical generation of hydrogen from water splitting, or PV, and then see if we can use that hydrogen effectively or not.
One more question. If you use graphene, only graphene, what will be the results? Have you tried? I know the prices are very high for graphene, but there are new progress on low-cost graphenes. If you use graphene only, what will be the results?
I haven't tried graphene as yet. The reduced graphene oxide is coming close to it, but it's not exactly graphene. So it'll be quite an interesting topic to try on this as well, subject. And I think I'll be happy to do some collaborative research with Sabancı University in the future if we can do some work on this. So I'll be happy to do some collaborations as well. I think there are 2 questions on the chat as well.
Emre Hocam, just thanks for the presentation.
Okay, thanks.
There is one now, and there is somebody raising hands. Hilal, you can ask your question. Then I'll read.
Thank you. Can you hear me?
Yes, yes.
Hello, Dr. Chakrabarti. It's Hilal Yıldırım Kalyon from Yıldız Technical University.
Yes.
I'd like to ask you, you're saying that you're using either activated carbon or carbon black. Have you used PVDF with them? Because we are using them, I'd like to ask you.
Did I stop the, sorry. 1 minute. Yes, maybe I was not very clear in my presentation. In this, I don't know if you can see the slide now, if I make it bigger. So this suspension that you see over here, which is the electrophoresis deposition reactor, is using combination of 90 weight % activated carbon and 10 weight % carbon black as it is. But then we're also applying some, we are saying polymer and charging agent. So if I'm using acetone as the solvent, then in addition to activated carbon and carbon black, we're also adding iodine as a charging agent, and we are applying PVDF as well, a certain portion, so that the PVDF acts as a binding agent once the activated carbon is deposited onto the aluminum foil electrode.
Okay, thank you. So you are using PVDF as a polymer agent. Thank you. I couldn't catch.
Yes, yeah. It's I think I was not very clear, but here I think I probably did mention. No, I didn't. I didn't put it here. Sorry. Yes, I was using PVDF, but I didn't mention it here. Sorry.
Okay, thank you.
Thank you for the question. And there is one on the checked box. Maybe I'll read it for you. normalization of the capacities was done by the volume. So is it the volume of the active material or the whole cell? That was a question from Ali Ansari.
The volume, is it for this flow battery system here, I think.
Ali, maybe you can clarify. It doesn't say. Yes, it is for the flow battery system.
Normalization of the capacity. I'll have a quick read. I can see is it done for the. Or it's the volume of the whole cell actually. Yes, that's the. Oops. Is there another
Okay.
one message here? Yeah.
Okay, thank you, Ali. Is there anybody? Maybe I cannot see the raised hands. If there is one, please speak up because I cannot see everybody on the screen. If not, I'll have a couple quick questions. You mentioned you are using a horizontal system for EPD. Is there any specific reasons for that? Because normal system is the vertical one. Is there specific like advantages of using a horizontal system?
The vertical system, when we tried it, it wasn't forming a uniform deposition for us. One thing I didn't mention here, we were using a binder-free system here for the flow batteries. So in this case, we started with reduced graphene oxide, and we made a colloidal suspension in DMF around 0.1 grams per liter, and then we sonicated it for about 1 to 2 hours, and then we tried to do a vertical deposition without any binding agent, and we found that it wasn't really sticking to the surface, and it wasn't very uniform, and the carbon paper was almost the same as before. And one of the reasons we thought was maybe because the graphene the reduced graphene oxide was aggregating and forming larger graphite particles. So then we thought, okay, if we try to do a horizontal way to keep the working electrode at the top, would that change the outcome or not? And we found that a few trials and errors, like amount of the deposition times to like 10 minutes, half an hour, 1 hour, the amount of voltage applied, like starting from 10 volts to 700 volts, we've managed to get 300 volts, by which we can actually 300 volts, 30 minutes. We managed to get the reduced graphene oxide particles to stick onto the surface of the carbon paper, and we managed to find good performance in the battery as well. And then when we made the same system with the nitrogen doped graphene, the same parameters also gave good performance. That's how
I believe gravity played a role in the vertical system as well. Yes. For the uniformity.
Yeah, exactly. That's the point. Yes, I think there's a question from
Tülay Hocam. Your sound, you are muted. Can you turn on the mic?
Okay. Have you checked particle size of your components with the results? Is there any direct relation with the particle sizes you use? Because there are different components, so it may affect the homogeneity, and you have some small holes, if I'm not mistaken, from your SEM results. Could it be because of the also particle sizes? You explained it as a evaporation of acetone, but could it be another reason with the, I mean, is there any relation about the particle size and the particle sizes, I mean, and the holes you observed in the SEM results?
We didn't do any direct particle size distribution analysis, but I think your point is, I agree with what you're saying. particle size does affect the deposition as well to an extent. The activated carbon particles are larger in size, about I forgot the size, some microns, whereas the carbon blacks go into hundreds of nanometers range, and the PVDF I forgot the size from the top of my head, but they do affect the amount of how the deposition occurs and the porosity of the sample, as you're rightly saying.
Porosity.
So
Not
I
the
think
holes, porosity, yes, of
porosity, yes. So I think this is something which can be investigated in the future. All these are still subject to further research. So what I have proposed and obtained over here is just initial results, and I think much more work can be done to optimize this further.
It may have a very high impact on the results, the end results.
Yes,
I mean,
yes.
capacitance results.
So I think, yes, so we need to do a proper particle size distribution and analysis as well, and tailor the electrodes accordingly from that. So thank you for this important point. Yes.
Yeah.
Okay, thank you. Any other questions? If not, I also have one more. For the fuel cell, for the flow battery results, you have an apparent increase in the performance of the coated surfaces. When you compare the results of our GO coated and doped graphite coated, is it the quality of the coating or the inherent properties of these two materials playing a role in those performances, like the conductivity, hydrophilicity of the materials you are using, or if they are giving a different quality coating on the carbon paper?
From the results in recent literature, they have always reported better performance due to higher charge transfer, especially if you have a nitrogen dope graphene gives better performance than just standard graphene in a vanadium flow battery. So in this case, we are comparing we're just modifying the vanadium side reactor with and so the hydrogen side is not tested as yet. So the vanadium side, it shows better wettability and also lower overpotentials when you're using the nitrogen dope graphene. So electrochemical performance improves when we use the nitrogen dope graphene. So it's probably not the coating, how do you say, the visual, whether it looks better or whether it looks worse or not. It's to do with the properties of the nitrogen dope graphene itself in comparison to graphene.
Okay. Yeah, apparently the conductivity plays an important role here, because nitrogen dope is even have better conductivity compared to the normal graphite or the RGO.
Yes, exactly. Yep.
Okay, great, thank you. One last question, a general one. Is there a limitation in terms of the thickness of the coating or the area of the surfaces, the substrates you can coat with this system, with electrophoretic deposition? You apparently managed to coat like 50 centimeters square surfaces for supercap.
That's for the supercapacitors, yes.
Yeah.
That there is always a limit depending upon the colloidal quality of the colloids formed in the solution. If it's not possible to maintain the activated carbon suspended in the electrolyte properly, then their thickness will start dropping with time, and it usually does happen. Although in some literature they do mention infinite thickness is possible. Obviously, that's theoretical calculations and all that, but with EPD. But in practical cases, it's not. There's always a limitation. And then when you start getting very thick layers, you also have problems with the porosity, tortuosity, and excess of electrolyte within the pores and so on. So there are a lot of factors that play a major part. So in some ways we are kind of fortunate that we managed to get a thick electrode and good performance, but we need to do more reproducibility studies to make sure that it can be something that we can recommend to the industries in the future.
The thickness is an important parameter for industry, I believe. They
Yes,
look for thicker coatings
Yes,
for
and-
high power systems, right?
Exactly, and also for long cycle lives as well.
Right.
They also do testing, like first we did 20,000 cycles in this case, but I think they can go up to even longer, like 50,000 and sometimes 100,000.
Yeah. Sure.
I think
Okay.
that Tulay Hanım has a
Tulay
question. I
Hanım,
think.
yeah. Do you have a specific lifetime tests? You made some cycle tests, but for the electrodes, do you have any specific lifetime tests so you can have some idea about the electrode life?
Electro lifetime test for the supercapacitors, you mean?
Yeah, for the supercapacitor. For fuel cell systems, there are some lifetime tests. That's why I'm asking. This is not fuel cell, I know,
Mhm.
but it's important for lifetime estimation. I mean.
Usually we do with the different cycle. For instance, at 0.1 amps per gram is quite a low current densities. So industries will be using 1 amp per gram, so even higher. And usually for supercapacitors, they will test the lifetime by the
Cycle.
charge and discharge and seeing how many cycles it can do.
Okay.
For especially at high current densities. In this case, one is because it's in our research, this is the first time we are showing this, so we are doing it at low current densities. But if future studies, I think we should take into account, as you said, lifetime studies as well as cycle lives as well.
Yeah. For real life, it will be important.
Yes, yeah.
Thank you.
Thank you.
Okay. Thank you, Dr. Chakrabarti, for this informative seminar. If there is no further questions, I also like to thank you for our participants for being with us today.
Thank you.
We can complete the session. Please go on.
If there are further questions, you can always email me at my university email, and whenever I have time, I'll try and respond.
Okay. Thank you. Thank you for this.
Thank you very much. I think there's one thing in the chat. Was that a question? Or no? Thank you.
It's a thank you.
Okay. Thank you very much.
Okay. Thank you, everybody. Until we see again next week for another Nano Open. And I believe we'll be in touch for further work with Dr. Chakrabarti. Okay.
Sure. Yeah. There's a lot of research to do for the hydrogen, vanadium, and manganese flow cells. So I think something we can take up further, and also supercapacitors.
Yes, exactly.
Thank you very much. Yeah.
Thank you again.
Thank you.
Have a nice day.
Yeah.
Everybody.
İyi günler.
İyi günler.
İyi günler.